Hello everyone, my name is Jason Molgaard and I'm a Principal Storage Solutions Architect at ARM. I'm here to speak today about flexible computational storage architectures. So quick agenda, let's take a look at the drivers behind computational storage, then delve into the details of controller architectures with Linux, look at some key workloads, and then wrap up. So what are the drivers behind computational storage? So one of the big reasons is bandwidth. With ever-increasing drive capacities, there's lots of data to be processed. So why move that data to the server when it can be processed right on the drive itself? This translates into a power savings, and that of course equates to a cost savings as well. There's a latency benefit with computational storage. You don't have to spend the time moving the data from the drive to the host CPU for compute. This improves reliability, just fewer moving parts, so to speak. And then it plays a role in security as well, because you don't have unencrypted data leaving the drive. So just to level set, what is computational storage? So if we take a look at these diagrams here, let me turn on my laser pointer. So we have this diagram here on the left that's kind of a traditional model SSD that would make a request from, a server would make a request to the storage. The storage would move the data to the compute. The server would perform the computations and then optionally move results back to the storage. With computational storage, the server makes a request to the storage itself performs the compute, and then results are returned to the server. This provides all of the benefits of energy efficiency, low latency, and security that I previously mentioned, but it also allows data-centric workloads to be deployed directly to the drive based upon the type of data that's stored on the drive. So the Storage Networking Industry Association Computational Storage Technical Working Group is working on a standard. This group was formed almost 2 years ago. ARM joined and helped found that organization. There are 45 participating companies today with about 211 representatives. There is a draft standard that's available publicly. You're welcome to go download it and take a look at what's been developed so far. And essentially, this technical working group is focused on a couple of different areas, both the hardware architecture, what are the definitions, what does an architecture look like for computational storage, but also software libraries and APIs so that everybody has kind of a common interface for how to determine what computational storage capabilities exist in a product, how to deploy them, how to use them, and just a overall standard from that perspective, so everybody's on the same playing field. So now let's get into the details of controller architectures with Linux. So if we look at a traditional SSD, it already has a significant amount of compute. So this block diagram here on the right is our SSD, and it's kind of broken up into a front end and a back end. That's kind of how typical controllers are developed, where the front end usually has host interface management and the flash translation layer management. The back end is typically the flash management for managing the flash channels. Of course, there's a significant amount of hardware accelerators built into that controller, encryption, LDPC, compression, all sorts of different things. And certainly a very large component in an SSD is the DRAM, and that certainly, if we try to draw that to correspond here in this picture, to the tune of 1 GB per terabyte of flash that's in the SSD. So today we're seeing drive capacities of 16, 32, 64 terabytes, and that likely translates into a 16, 32, and 64 gigabytes of DRAM in that drive, a significant amount of DRAM. So this drive, this traditional SSD, already has a significant amount of autonomous processing on the drive. So the host today sends LBAs, logical block addresses, to the drive, and the drive converts those to physical addresses for where the data is actually stored on the media. The drive also stores the file system that the host uses to map files to LBAs. So if you have a drive, a computational storage drive, With Linux running on the drive, now the drive is capable of not only mounting that file system and recognizing the files, but can then convert those LBAs into the physical addresses needed to actually find the data on the drive. And of course, it can now perform any compute operation that was previously run on the host. You can do it either in real time as the data is streaming in or out, or after the fact by pulling the data out of the drive media and performing operations on it in place. So why Linux? Other than the benefit I already mentioned about being able to mount the file system, which is certainly a big one, why have Linux at all? Well, certainly I think we can agree Linux is quite ubiquitous. There are standard versions, tiny versions, huge open source developer community. It's very, very prevalent, very ubiquitous. So Linux is going to work with whatever computational storage drive standards come out of the SNIA technical working group. There won't really need to be any changes whatsoever for that Linux support. Workloads can be deployed to the drive using standard tools that are readily available, like Docker or Kubernetes. And security is a solved problem on Linux. It's well understood and will certainly contribute to ensuring that our computational storage drive is secure as well. There's a vast ecosystem of ported and optimized software for running on Linux. So all the standard administration tools, containerization, protocols like TCP/IP, NVMe, databases, machine learning, all this is readily available and quite supported on Linux. So let's take a look at options to add on Drive Linux. So if we take a look at these diagrams over here on the right-hand side, starting with this one on the top, this box that I'm kind of circling with my laser pointer, this is a traditional SSD where we have our front end that we mentioned previously and our back end, a PCIe interface. And this is a daughter card or an interposer that would connect up to it. And on this daughter card is an applications processor. Data can be moved from the drive across this PCIe interface into the applications processor for compute, and results can certainly be sent back. So this is a great proof of concept for computational storage, leveraging existing SSDs today with a small little daughter card, but it has some challenges. Certainly one big challenge is the fact that there's a back-to-back PCIe interface. So we're not saving any of the bandwidth that I had mentioned previously. We still have to package the user data up in NVMe, in PCIe, move it across this interface, unpackage it at the other end, perform the computation. Certainly that takes a lot of bandwidth, power, time, and doesn't really solve any of the latency challenges. This applications processor also requires its own non-volatile memory storage to boot the Linux, and likely its own DRAM. So to solve a lot of those challenges, we need to take a look at this middle box here. So this box here is our same SSD with the front end and the back end processor. But now we've incorporated that applications processor into the same controller as the rest of the SSD functionality. We've eliminated the back-to-back PCIe interfaces, so that saves all that bandwidth of moving the data back and forth. This applications processor is now able to share the same DRAM as the rest of the SSD controller, and of course can share the same non-volatile storage, the flash media itself, for storing the Linux. So this is great. Lots of existing products today, or several existing products today, based upon this kind of architecture. The next logical progression then is, well, why not combine the applications processor and the front end processor into one cluster? And that's exactly what this diagram here on the bottom is showing, where the applications and front end processors have been combined. And of course, this provides additional area benefit, cost savings for the controller itself, which just lowers the overall product cost. So taking a look at Linux, one recent version of Linux, the Debian 9 version, has these system requirements. So 128 megabytes of RAM minimum, 512 recommended, and 2 gigabytes of storage. So this is actually very small, all things considered, when compared with the SSD itself, less than 5% of the storage. If we take a typical 16 terabyte SSD with 16 gigabytes of DRAM, We're using less than 5% of that for the Linux operation. And of course, we've got 16 terabytes of storage, so using 2 gigabytes is also quite small in the grand scheme of the overall storage capacity. So kind of extrapolating a little bit, if we look at this picture here on the left, we essentially have our controller with 4 real-time cores showing, and that traditional SSD takes all of the data that's stored on the media, sends it across to the host, and the host does the processing. With computational storage, over here on the right-hand side, we want to be able to take the controller and allocate some of the cores for doing computation right on the data. Of course, we still need to be able to send all the data to the host if necessary, but we want to extract the insight right from the data, find what we're looking for, or perform the operation, and just send the results, send the insight to the host CPU. So taking that a step further, we want to even have flexibility to change the balance of that workload over time. So perhaps during very peak times of the day, when the drive is especially busy, maybe there's 0 cores or 1 core at most allocated to performing compute of the data that's stored on the drive, and the rest of the cores are purposed for managing the transfers in and out of the drive. But later on, during off-peak times, we can repurpose some of those cores to running Linux and performing the compute on the drive within the same controller. And so if we kind of step back and say, what have we created? I would suggest we've really just created a low-cost edge server. If we look at this picture over here on the right-hand side, it's an edge server with an SSD connected to it. So here's our edge server. So this PCIe, CPU, DRAM, and a network interface. And then this PCIe, flash, CPU, DRAM, that's our SSD. Well, we've now deployed on those CPUs Linux. We can substitute a TCP/IP interface for the PCIe and run running Linux on that drive and use NVMe over fabrics to speak to the outside world. And we've effectively created this, where we've got our flash media, our CPU, and our DRAM speaking across a network interface. It's essentially a very low cost, small edge server. So computational storage scales and collaborates very nicely, especially as more capacity is added to systems. So looking at this little picture here on the left, we've got 4 computational storage drives, each of course with its own compute, offloading this host CPU. If we find that that's no longer enough capacity and we need to double our storage capacity, shown over here, now we have 8 drives, we've doubled our compute in those drives. And all these drives are capable of working in parallel on a particular workload to offload this host. So work can be getting done on all these drives at the exact same time in order to get tasks done as fast as possible. So one of the things that we're in the process of investigating in ARM is a Hadoop cluster with those types of computational storage drives, and what would the software stack look like? What would the overall architecture look like? So here's kind of a slide that speaks to our thoughts and what we've been working on. I don't really have any results to share today, but when we do, I'll be happy to give an update on that at a future time. So let's take a look at the key workloads. So there's lots of workloads listed here, and we can come up with lots of different examples. So offload, compression, encryption, encoding are certainly some very obvious and key workloads. Database acceleration is another one. You know, if you've got this very large database of information, whatever that information may be, why move all that information from the database to the server in order to perform a query and search? Content delivery network is another great example where maybe you've got your movies that you want to stream to various devices, and on the drive itself, you can re-encode the data at various bit rates in order to for the different size screens that users are using to view that content. Image classification is a great one for computational storage, running machine learning type workloads to look for images or types of patterns in images. Transportation with lots of telemetry data in airplanes, for example, and high definition map data for autonomous vehicles moving forward. So lots of applications for computational storage. So to kind of conclude, computational storage is happening today. The SNIA, the technical working group, Computational Storage Technical Working Group, is developing a standard to deploy and manage workloads. Linux, we believe it delivers the fastest route for workload development, deployment, management, because everything is ported and just works. And compute scales as drives are added. Each computational storage drive that you add allows more cores to work in parallel. Thank you.